Hi there. During this session I'm going to be talking about heat capacity and specific heat capacity. I'm going to start off with you thinking about a situation. Imagine that I was cooking a Sunday roast. So I placed some food into the oven. In fact, I placed a chicken. Think about this. If I provide heat energy from my oven, what will happen to the temperature of my chicken? Clearly you're going to recognize that the temperature of the chicken is going to go up. Now, will the temperature of the potatoes increase at the same rate? That's the question there. Now, we're talking about the increase in temperature. Okay, when they reach a final temperature, when they're in thermal equilibrium, everything will be the same. But what about the change in temperature? So what do you think is going to happen here? Now, what actually happens is a body with a high heat capacity will take in thermal energy at a slower rate than a substance with a low heat capacity, because it needs more time to absorb a greater quantity of thermal energy. And that means that the two objects, as they have different heat capacities, will increase their temperature at a different rate. Let's look at this in a more mathematical way, but as well as remember heating up, it also means when you take the food out of the oven, it's likely to cool down at different rates as well, and this reflects the same concept, and that's one of heat capacity. So let's talk about that in more detail. Now, heat capacity is how much energy it takes to raise the temperature of an object by 1 degree Kelvin. If we look at it mathematically, the heat capacity, shown here as capital H, it's often shown as a capital C as well in many cases, is equal to the amount of energy added in joules divided by the change in temperature, Kelvin. And that gives us what's known as the heat capacity of an object. To put it into a problem, the heat capacity of a sphere is 3000 joules per Kelvin. How much thermal energy heat is released as the temperature drops from 400 to 300 degrees Kelvin? Now what I have here is I know what the heat capacity is, and I know that the change in temperature is 100 degrees Kelvin. So if I multiply those two values together, I work out that 300,000 joules is the amount of thermal energy which is released in this situation. One of the snags we have here with heat capacity is it's just dependent on an object. Now, if we think about it, we'd imagine that a big object of one material compared to a small object of another material will require less energy. So if we take into consideration mass, it brings us to our next step, which is specific heat capacity. Now, specific heat capacity incorporates mass, and it is the energy required to raise 1 kilogram of an object by 1 degree Kelvin. So if we look at this mathematically, the quantity of heat transferred, shown as letter Q, is equal to the mass of the object, the specific heat of the material, so the specific heat capacity is often shown as a small c, multiplied by the change in temperature. Looking at specific heat capacities in comparison with others, we realise that every material has a specific heat capacity. And another thing to notice here is how in different states, for instance water, has a different heat capacity for liquid, ice and steam. These different heat capacities are all due to the structure of the different materials, and are definitely impacted by the fact that in different states you'll find that the molecules will require a different amount of energy to increase their internal energy because of the different potentials between the molecules. The key thing here is that you've got to remember that every substance has a different specific heat capacity in each state. Let's try and use this formula to do a calculation now. I've got a 2 kilogram cylinder of copper, and it's heated from room temperature, 20 degrees centigrade, to 500 degrees centigrade. 374 kilojoules of thermal energy was transferred to the copper during the heating process. can we calculate the specific heat capacity of the piece of copper. Now what we have to do here is rearrange our formula. We know what the amount of energy going in is, we know what the mass is, and we know what the change in temperature. So my change in temperature is 500 minus 20. Now note here that I'm quite happily using degrees centigrade here, because that change in temperature, degrees centigrade, is actually equal to 480 degrees Kelvin, because remember the size of a centigrade and the size of 1 Kelvin is exactly the same. So putting my numbers in, I get a specific heat capacity for copper. This is copper as in a general form, not dependent on its mass, is 390 joules per kilogram per centigrade. And that means that 390 joules are needed to raise the temperature of 1 kilogram of copper by 1 degree centigrade. Hopefully that gives you an insight